All right. And we are live. Let's give people a minute to join. Oops. Need to turn off the sound on my end from the stream. I always have the stream in the background so I can see the chat. All right, so let's have a look at today's challenge. Let me, it's a little different. We'll do it like this. All right, so we are gonna have a look at challenge number 15. So we've got lens library. The newly focused parabolic reflector dish is sending all the collected light into a point on the side of yet another mountain, the largest mountain on Lava Island. As you approach the mountain, you find that the light is being collected by the wall of a large facility embedded in the mountainside. You find a door under a large sign that says lava production facility, and next to a smaller sign that says danger, personal protective equipment required beyond this point. As you step inside, you are immediately greeted by a somewhat panicked reindeer wearing goggles and loose-fitted hard hat. The reindeer leads you to a shelf of goggles and hard hats. You quickly find some that fit, and then further into the facility. At one point, you pass a button with a faint snout mark and the label "Push for Help." No wonder you were loaded into that tree budget so quickly. You pass through a final set of doors surrounded with even more warning signs and into what must be the room that collects all of the light from outside. As you admire the large assortment of lenses available to further focus the light, the reindeer brings you a book titled Initialization Manual. Hello, the book cheerfully begins, apparently unaware of the concerned reindeer reading over your shoulder. This procedure will let you bring the lava production facility online, all without burning or melting any unintended. Before you begin, please be prepared to use the holoday ASCII string helper algorithm Appendix 1A. You turn into Appendix 1A. The reindeer leans closer with interest. The hash algorithm is a way to turn any string of characters into a single number in the range 0 to 255. To run the hash algorithm on a string, start with the current value of 0. Then for each character in the string starting from the beginning, determine the ASCII code for the current character of the string. Increase the current value by the ASCII code you just determined. Set the current value to itself multiplied by 17. Set the current value of the remainder of dividing itself by 256. After following these steps for each character in the string in order, the current value is the output of the hash algorithm. Okay, that doesn't sound too complicated. So the way to find the result of running the hash algorithm on the string hash, the current value starts at 0. The first character is H. Its ASCII code is 72. The current value increases to 72. Current value is multiplied by 17 to become 1224. The current value becomes 200. The remainder of, so this is a module. The next character is A. Its ASCII code is 56. So what do we do with the hello Matthias. So let's make sure we understand this. So we have 200, and because this is a with 2 plus this, so we just keep continuing with the same thing, and we just start with the current value at 0. Okay, it's not too bad. Okay, so the result, yeah, okay, the initialization sequence, your puzzle input, the comma separated Matthias says, I have no idea what's happening. First time seeing Advent of Code on day 15 this year. Yeah, I'm also the first time I'm looking at this. Every time I do this, this is the very first time you're seeing me read this. So the initialization sequence is a comma separated list of steps to start the lava production facility. Ignore new line characters when parsing the initialization sequence. To verify that your hash algorithm is correct, the book offers the sum of the result of running the hash algorithm on each step. Okay, so we need to build this hash function, and then what did it say? This initialization sequence specifies 11 individual steps. The result of running the hash algorithm on each of the steps is as follows. Rn equals 1 becomes 30. I feel like I missed reading something. Wait, so we just run the hash on this full input, I assume. Okay, so and this, okay, and then we sum the all the hashes together. Okay, so then let's get our puzzle input. And we'll start. All right, so we read our input. Let's just do read file. And we'll just do what's this called? Initialization sequence. So we just do parts is string dot split and a comma, and then we want our hash function is a character, and we return. Okay, we can do that, but how did it go again? So we take the ASCII code, then we multiply it by 17, and we do 156. That's our hash function. We do current value 0, and we range over our part, and we sum that up. Did I understand that right? Okay, let's see. Okay, is that it already? That doesn't seem right. Putting out the int. Okay, oops, and we of course wanna print. See, that is not the right answer. Full. Okay. Go back. Okay, so it said something about make sure to use all of it. It did say something about line breaks, I think. Ignore new line characters. Sorry, ignore new line characters. So we just remove them. Okay, so we first wanna dot replace all. Oops. Same value. Okay, let's test this smaller one for a second. So we comment this on. And let's just do this. What? We just did something super silly, super wrong here. So the hash function was wrong here. So we oops. we need to continue doing this. It's not. I just made a mistake here. So for each and then we do hash plus equals that. Then we do oh, and then we return h. Okay, and then that, and then let's just try this real quick. Okay, that's a different value. Okay, that was the right answer. Then let's continue with part 2. All right. So you convinced the reindeer to bring you the page. The page confirms that your hash algorithm is working. The book goes on to describe a series of 256 boxes numbered 0 through 255. The boxes are arranged in a line starting from the point where light enters the facility. The boxes have holes that allow light to pass from one box to the next all the way down the line. Inside each box, there are several lens slots that will keep a lens correctly positioned to focus light passing through the box. The side of each box has a panel that opens to allow you to insert or remove lenses as necessary. Along the wall, running parallel to the boxes, is a large library containing lenses organized by focal length, ranging from 1 through 9. The reindeer also brings you a small handheld label printer. The book goes on to explain how to perform each step in the initialization sequence, a process it calls the Holiday ASCII Helper Manual Arrangement Procedure, or HashMap for short. Each step begins with a sequence of letters that indicate the label of the lens on which the step operates. The result of running the hash algorithm on the label indicates the correct box for that step. The label will be immediately followed by a character that indicates the operation to perform. Okay, so what we previously saw was a label and then some operation. If the operation character is a dash, go to the relevant box and remove the lens with the given label. If it is present in the box, then remove any remaining lenses as far forward in the box as they can go without changing their order, filling any space made by removing the indicated lens. If no lens in that box has the given label, nothing happens. If the operation character is an equal sign, it will be followed by a number indicating the focal length of the lens that needs to go into the relevant box. Be sure to use the label maker to mark the lens with the label given in the beginning of the step so you can find it later. There are two possible situations. If there's already a lens in the box with the same label, replace the old lens with the new lens. Remove the old lens and put the new lens in its place, not moving any other lenses in the box. If there's not already a lens in the box with the same label, add the lens to the box immediately behind any lenses already in the box. Don't move any of the other lenses when you do this. If there aren't any lenses in the box, the new lens goes all the way to the front of the box. If there aren't any lenses in the box. Okay, sure. Okay, so I think I need to read some of this again. So what happens with the number? So Rn is the label, and the equal sign means so it goes in the relevant box. So basically, we have boxes that are 256 boxes, and then we have lenses, and our lens is uh, we have a focal length, but we also have the operation character. Okay, so here is the contents of every box after each step. At the end of the above example, the focusing power of each lens is as follows. So that's the sum of these. So we need to again keep some counter here. One plus the number box. Confusing. So let's take this one thing at a time. Each step begins with a sequence of letters that indicate the label. So a part is either it either ends with a minus or the second to last character is an equal sign. Okay, so those are the two things. So that also means that the label is that, and here label is that. How do we know the relevant box? What? The boxes are arranged in a line starting from the point where the light enters the facility. Okay. Each step begins with a sequence of letters. The label of the lens on which the step operates. The result of running the hash algorithm on the label indicates the correct box, and that's okay. So let's do this then, and we'll initialize this because it said the boxes are always present. And so the box is, yeah, exactly that. And same here. So if it's a dash, go to the relevant box and remove the lens with the given label. So we'll do a find function. Label string. We'll return the index, I guess. Yeah, and we just search for it, and yeah. And so in this case, we actually want to remove it. So I'll remove label string. Yeah, we find it, and yeah, exactly. Remove it like this. Okay, that's good. So we then do box.remove. Yeah, okay. And in the other case, we do what? If the operation character is an equal sign, it will be followed by a number indicating the focal length of the lens that needs to go into the relevant box. Be sure to use the label maker to mark the lens with the label given in the beginning of the step so you can find it later. If there is already a lens, the same label, replace the old lens with the new lens, remove the old lens and put the new lens in its place, not moving any other. Okay. Okay, so then we'll do this as well. And we'll do set label string and what is it, focal length? So we'll first find, so if it's not there, if it's not already there in the box with the same label, add the lens to the box immediately behind any lenses already in the box. Don't move. There are yeah, okay, that okay, and yeah, okay, cool. That's exactly what we want. We want the, in this case, if we haven't, if this label does not exist, we add it and we add a new one, and otherwise we just modify the focal length in exactly that spot without moving anything. All right, so then we need to call box.set with the label and the focal length. No, current value is wrong. We need to parse the value from that. So in this case, we need to let's write a quick function. Parse focal length, and it's a single character. So we just do we return C do that. I think that's it. So we're just gonna take the code point of 0 and subtract that from the rune. Okay. So we do parse focal length and we use the last character exactly. Okay, so But what do we then do? This I didn't understand yet. Okay, so I think now we should have all the boxes correctly initialized. Aha, okay, so given the position within the box, we multiply. Wait, what? The slot number of the lens within the first lens. Because R and because this is 1. And just to make sure that I understand this correctly, 4 sorry, did the 4 now come from here, or did the 4 come from... That would make logical sense though, no? The slot number with the lens within the box, 1 for the first lens, 2, yeah. Okay, so we're just starting with 1, I assume. So we do... yeah, so we range over the boxes. So current value starts with 1. And we hold up. So this is all of these combined. It's a long text this time. I think we've got this right. Within each box, lenses are listed. Okay, so we're first gonna want to if length of lens is 0, we continue. So what is the input to the next box? That's what I'm still trying to figure out. Oops. One plus the box number of the lens in question. To confirm that all the lenses are installed correctly, add up the focusing power of all the lenses. The focusing power of a single lens is the result of multiplying together 1 plus the box number. Oh, sorry. Okay, this I 1 plus the box number. Okay, so that's why it's 4 here. Oh, I just didn't read correctly. Then the slot, then the focal length. Okay, so that's just adding all of this together. So it's for each lens we do, so we need the box number here, and we will need the lens number as well, right? Yes, we need the slot number. Okay, so the current value is and we do the box number, which is I plus 1, and we multiply that with the j plus 1, and we multiply that with the focal length. Okay. And then we sum them all up. Maybe this is right? Let's see. Okay, so we have a number. Let's see if this is right. That's not the right answer. If you're stuck, make sure you're using the full input data. Okay. Oops, no, sorry. I didn't want to put that. So if the operation character is a dash, go to the relevant box and then remove the lens with the given label. Let's see if we. So we initialize all of our boxes, and then we let's just focal length this. Okay. Let's see. CNF3 ZPPRKV VK0. Yeah. Okay. I think we've got, let's say the instructions correctly. So these are instructions. Instruction. Hmm. Yeah. I should have just used Go rename. Silly of me to do it like this. Wait a second. I think I did the initialization wrong here. So that's one less. That is the right answer. Okay. That was just the initialization that I did incorrectly first. Okay. All right, so let's have a look at this then. First of all, let's commit this. Whoops, I also forgot to commit last time. Do not recommend this, but I'm just gonna do this. Commit day 15 or 2. Now, since this is Let's Profile, let's have a look at how could we make this faster. Now, I mean, let's write a benchmark, right? We want to let's assume that we already have all of this input and we remove the character. So we'll focus on just this part. So benchmark. What shall we call it? Benchmark instruction. I don't know. Let's stick with this. We change it to that. Do this. Actually, I think I kind of like keeping that part. So we'll just do this. And let's extract all of this. Arrange boxes. And we pass. Sorry, no, it was called initialize something. What was it called? Initialize. We'll just call it initialize then. Initialize. And we return an integer. That is our. All right, so we have our input that is a byte slice. And we don't care what it returns, but we want to initialize. Okay, so let's call it content then. All right, so let's just make sure that this still works. Okay, we need to return value. That's important. So now we go test run. We ignore everything except for our benchmark. And let's see if that works. Okay, so we've got some baseline. So let's put that into here. And we'll also do this a couple of times, and we'll also output some profiling data. So it looks like we have a fair amount of stuff that's happening, but let's see. So we upload our profiling data, and here we go. As always, let me know if anything about the font or anything isn't large enough. But here we go. So it looks like the first thing, so of course everything, the whole time is spent in our initialize function. Looks like the string splitting is already very expensive. Then we do our hashing. I don't know if we can make this significantly faster, but we'll look. So definitely the string splitting is something that we're gonna want to look into. And then, all right, these boxes definitely also, we're doing a bunch of allocations here. Not sure. So this is the set function. Where we're doing some allocations. I think this is largely looking good. This is interesting. I would have actually expected fine to be more expensive, but it's still decent. It's still like 12% of all of the CPU time. But the string splitting, it looks like, is going to be our biggest win at the start. So let's start with that one. All right, so the reason this is the case is, as we can see, it's, oh, interesting. It's actually making the slice is not very expensive. And here is slice byte to string. Okay, interesting. So there's some time spent in this, but it's not actually very major. Good that we measured this. So there's some amount of time being spent in generating that slice, but it's actually not very bad. Okay, maybe we should look at the find function after all. We're growing some slices here. We could do better with initialization, I suppose, but it's not that bad. %2 only. All right, then I guess let's focus on find. Okay, so that means, we did a pretty naive search here. We just did a linear search over the box. So instead, what we should then do is we should have an index that maps the label to the integer, or I suppose, could we yeah, I guess we can do the lens directly. Or yeah. Because so if we set, so we want to change this, the find function then to be the lens instead. And so if that's nil, we append and set our index to, maybe we can do this separately here. I like that better. We do that, and then index label our lens. Let's actually call it lens. And otherwise, let's do it like this. Otherwise, we just do lens. Okay, maybe that's why we should do. Maybe I. So. Okay, never mind. We should have left this as the index. And put the index here. And our find then becomes, we do box index with label, and we do I and found, and if not found, we return -1. Let's finish that again. And otherwise we return I. So when we do that, -1, lens, and lens, and here we do length of lens, yeah, -1. Okay. Let's add our test bag actually. Test instructions. Our value, and we equals our value. I forgot what it was. What? Yes, Matthias was saying this is where the fun begins. I agree. All right, so now let's just run our test that this still works correctly. We did not initialize our map, of course. Classic. Let's try that again. Index out of range. In 36. Oh, we did not remove. Delete. Yeah, exactly. What did we do wrong now? So let's just go through this logically. If we set something, oh, we need to actually move. We need to actually move all the lenses. Okay. We need to take these lenses. We don't care about the index, but we care about the length because we want to know the label. And for all the indexes, we want to remove them by one exactly. So we need to range here, of course. Let's see. All right, that did the trick. Yes. So we needed to adjust this. So let's see if this is actually any faster, right? Maybe we made it worse. We'll see. I don't remember the numbers from last time, so let's bench that. Compare. All right, so we got worse. And that is because of the map, I assume. So let's... Yeah, so the map access and map assigning is actually getting worse, making it worse. Interesting. But yeah, I suppose it makes sense. Oops. Let's do this directory. So previously we were doing a linear search, but the linear search is actually pretty good because there are only a few lenses at a time. Interesting. Okay, so let's we'll I kind of like the benchmarking setup that we have though. So I'm gonna just no, we don't want to discard that. Yes, we want to discard that. Yes. Not with this, we want to split. Yes, we want to discard that. Yes, we want to discard that. Yes, we're going to discard that. Yes, we want to discard that. No, we don't want to discard that. No, we don't want to discard that. Yes, we want to discard that. And no, we don't want to discard that. So let's see this again. This should now be identical again to what we had before, but just making sure. Roughly the same. This could just be the tiny changes that. Okay, so. All right. Interesting. So let's go back to profiling data then. So finding growing the slice, creating new object. So if this was production code, if I see something like this, I would probably, and it was actually like something that I wanted to improve for latency or something like that, I would probably introduce a like a pool here so that we don't have to keep allocating new objects, or we can just allocate a bunch of objects at the start. But it looks like here, not really. I mean, we could do it, but just for the exercise of it, but I don't know if it really makes that much sense. Part one. We could have a look if there's something that we can do in the hash. I don't really think so. So this was our hash. We have to do these things sequentially. That's how the hash function works. There's some micro optimizations here and there that we could do. Like we could pre-allocate these boxes all at once by doing something like this, and then using the pointer to each of them. That way we do one allocation for 256, but probably not very effective. Like I said, this where is it? This allocation is the one that makes a difference, as we can see here. And the growing the slice is maybe worth it as well, as we can see here. But overall, looks like we actually started out with a pretty good implementation, and I think I wouldn't typically optimize more here unless this was, very, very performance critical. I think this is where I would kind of stop typically. So yeah, that's it. That's Advent of Code challenge day number 15. Hopefully you learned something also having a look at this profiling data. So with that, happy profiling, and this may be the last episode for the end of the year. So hope you have a great start into the new year. Hope you can get some rest over the holidays. And with that, happy profiling. Please give this a thumbs up and subscribe, and see you next year. Thanks, everyone. Bye-bye.